My name is Jonathan, and I'm going to tell you about some thoughts my co-authors and I have had about using PL techniques to make it easier to implement high-performance, correct cryptographic protocols. Our hypothesis is that enforcing a language-level separation between the high-level structure and the low-level details of protocols will help both with optimization and with verification. To start, let's talk about how people implement crypto today. On the one hand, if we're prototyping a new protocol, we probably want to use a language that looks like the mathematical specification. For example, the computer algebra system SAGE exposes algebraic primitives like finite fields and elliptic curves, which closely match the abstractions used by protocols. And then on the other side, we might want to implement cryptography to be deployed, which is a bit more complicated. The code has to be high performance and it needs to be secure, which could mean, for instance, that some parts of the protocol need to be constant time. To get all these properties, implementers of deployed high-performance crypto typically use a combination of low-level languages like C and assembly. Let's actually see how deployed crypto looks different from the prototype code we talked about before. If we were prototyping a Schnorr signature in SAGE, we would first need to define an elliptic curve, which SAGE lets us do in a compact way. Here, we define f to be a field with cardinality p, and then later on, we define e to be an elliptic curve. In particular, e is a widely used curve called curve 25519. Using these primitives, it's very easy to write down the signing procedure. This line expresses an elliptic curve scalar multiplication, and the important thing here is that the code closely matches the mathematical description. This is a very high level of abstraction. Under the hood, a scalar multiplication is a bunch of point additions, and each point addition is a bunch of field operations. So clearly, SAGE is a nice tool for prototyping protocols, but you could never ever deploy this implementation. In the real world, you need your implementation to be fast, and for security, you also need properties like constant timeness, neither of which you can get from SAGE. So now let's look at an example library that is actually deployed. This is libsodium, which is written in C and assembly. Since these languages don't give us any of the cryptographic primitives we need, we have to create them ourselves. This code is part of the implementation of field operations. It uses a lot of low-level bit twiddling, both for speed and to try to remain constant time. Once we built all of the primitives like this one that we need, we can put them together. This is the libsodium version of the sign function that we looked at before. But unfortunately, it doesn't really look anything like the paper description of the protocol, because it mixes high and low-level abstractions. For example, it intersperses elliptic curve operations with memory management. In principle, we could use libraries for low-level functionality, and we could build really beautiful abstractions to make the code look like the math. But all that ends up being programmer discipline. The compiler doesn't know about these abstractions, so it can't help us enforce them. And there's another problem hiding here. Imagine we want to prototype a protocol and then deploy it. First, we have to manually translate the SAGE into C, and then we just throw out the SAGE code. This process wastes effort and creates more opportunities to make mistakes. To address all of these problems, we've begun to design and implement a language called Parseltongue. The goal of Parseltongue is to make it easy to both prototype and deploy new protocols. The first thing to know about Parseltongue is that it is actually a family of languages. There's an interpreted version for prototyping protocols called interparsel, and a compiled version for generating deployable implementations called comparsel. As we'll see, it's relatively easy to go from a prototype to deployable code that is high performance and possibly compiler optimized and/or verified. Continuing our example from before, let's see how we can write a prototype implementation of Schnorr signatures in Parseltongue. and then how we can turn that prototype into something deployable. As a first step, let's turn the mathematical description into a prototype. The textbook description of a Schnorr signature starts, let G be a cyclic group with order Q and generator P and G, and let H be a random oracle to FQ. In Parseltongue, we have a standard library of cryptographic primitives, or abstractions that are commonly used in cryptography, like the cyclic group and random oracle that this Schnorr signature description talks about. These primitives are type classes in the language, and they have a carefully chosen default implementation. This allows us to prototype a protocol in interparsel without needing to specify an implementation. Here, we define a cyclic group G and a random oracle H in this interparsel code. Note that in interparsel, we can define G to be an arbitrary cyclic group, whereas in Sage, we had to define G to be an elliptic curve. This generality is more faithful to the textbook description and has other benefits that we'll discuss later. Now we can implement the same sign procedure that we saw in Sage. Similarly to Sage, the interparsel code looks a lot like the textbook description, but underneath the mathematical abstractions, things are a lot different from Sage. Let's see how. On the left is the sign function we just wrote in interparsel. The main difference between this interparsel script and a comparsel program is that in comparsel, we need to specify type information. On the right, we've added type annotations. Looking at the type signature of the function, we can see that pk, the public key, is a group element, sk, the secret key, is a scalar, message is the string to sign, and the result is a tuple containing a group element and a scalar. Now we need to define what these types are. G, the group, was previously an object, but now becomes a type variable, which must be bound to a type that implements the additive cyclic group type class. Then, E and F are defined in terms of the group G. In other words, this implementation is generic over any additive cyclic group. To run this code, we need to actually implement a high-performance additive cyclic group for our deployed code to use. Let's say we want to build an implementation of curve 25519 to use for signing. We would first define the representation and operations, for example, using comparsel primitives or by linking to an existing library written in another language. And then we would implement an instance of additive cyclic group for curve 25519. Even though our Schnorr signature uses this high-performance primitive, the low-level description of the primitive is still separate from the high-level description of the protocol. This distinction makes it possible to quickly swap out primitive implementations, or to choose between many implementations, say based on the underlying processor architecture. But we don't just have to rely on primitives that are hand-tuned for performance and correctness. The compiler, now that it has type information, can use any number of standard optimizations that are already implemented, say in LLVM. But not all of these optimizations will work out of the box. Some of them might break constant timeness. To deal with this, comparsel lets the programmer specify which values are secret. For example, in the Schnorr signature, both the secret key and the nonce are secret, and the compiler can use these secrecy labels to do a ton of work for us. It can use known techniques to generate constant time assembly from high-level code that includes control flow, and it can also optimize and manage memory in a way that's timing safe. Beyond performance and basic correctness, we might want stronger guarantees. And one way of getting those guarantees is by using verified versions of primitives, say written in Jasmine or F*. But what about compositions of primitives, or even compositions of protocols themselves? To start to answer this question, let's take a quick detour and talk about a cryptographic framework known as Universal Composability, or UC for short. Skipping most of the details, if we prove that a protocol is UC secure, That means that it is indistinguishable from an ideal black box model called an ideal functionality. The payoff for using UC is that it gives us strong guarantees about how we can compose UC secure protocols. Specifically, composing two UC secure protocols is at least as secure as composing their corresponding ideal functionalities. We can think about the UC composition theorem as being analogous to a secure linker, and the UC framework tells us precisely the properties we need from this linker in order to securely compose protocols. We hypothesize that we can capture UC ideal functionalities by extending the notion of a type class. For example, we could imagine capturing the UC definition of a signature scheme as the UC signature type class. Then, when we instantiate UC signature, we must prove that the concrete protocol UC realizes the ideal functionality. Once we've done that, we can safely use UC signature in higher level protocols, as long as Parseltongue provides a secure linking functionality. The UC composition theorem tells us precisely what properties our linker needs to be secure. And, of course, one of the future goals is to prove that Parseltongue's linker actually provides those properties. Now, let's see a simple Diffie-Hellman key exchange running in Parseltongue. The protocol code is on the left. We still use a cyclic group, just like in Schnorr signatures. But now we'll see some new primitives too. First, the cipher primitive lets us use symmetric cryptography. Next, since this is a key exchange, we also need interactivity. Much as interactivity is explicit in protocol diagrams on paper, interactivity is explicit in Parseltongue as well. In this protocol, there are two parties, Alice and Bob, who can exchange messages using the other party's handle. Alice sends to and receives from Bob, and vice versa. The way Alice and Bob send and receive is totally abstract here. The description does not depend on how the network is implemented. In fact, before we implemented real network communication, our first version communicated over the local file system, and replacing the file system with a network didn't require any changes to the protocol itself. Parties like Alice and Bob in this code are the entry points to a protocol's execution. To run the protocol, we execute both parties, and they find one another on the network using the Prisk demo session ID that we supply on the command line. Now let's execute the protocol. Alice and Bob first generate a shared secret, which Alice uses to encrypt her password. Then, Bob decrypts the password and prints it to the terminal. Wrapping up, Parseltongue's goal is to make it easy to go from prototypes to deployable code by separating high-level structure from low-level implementation details, and keeping all of that information available to the compiler. Our hypothesis is that maintaining and enforcing this explicit separation will make both optimization and verification easier. Thanks for your time. I'm happy to take questions.